This is a GET problem that came in the instrumentation engineering paper, but you can expect similar problems for electrical engineering as well as EC papers. So this is a problem from Zener diode. The question is stated like so. Assuming Zener diode D1 has current voltage characteristic as shown below and forward voltage drop of diode D2 is 0.7 volt, the voltage V0 in the circuit shown below is option A 3.7 volt, option B 2.7 volt, option C 2.2 volt, and option D is 0 volt. So this is the circuit. It has a Zener diode and a rectifier diode, and this is the voltage current behavior for the Zener diode. So if we look at this question, the information that we are provided with is that the forward voltage drop of the diode D2 is 0.7 volt. So this diode D2 will incur a voltage drop of 0.7 volt if it is in forward biased condition. And this is the characteristic of the Zener diode. And so in the reverse bias region, we can see that the breakdown voltage is equal to 2.7 volt. And from the position of this Zener diode D1, we understand that this will always be in reverse bias mode. This is not in forward bias condition. So this first quadrant is irrelevant to us. Now, solving for these sort of questions where you have a DC source and a Zener diode, I had mentioned it in one of my previous videos that you have to first of all identify the state of the diode. So identifying the state of the diode means that we have to know whether the diode has moved into this reverse bias conduction mode or whether it is in non-conduction state. So this is the non-conduction state, whereas this is the conduction state in the reverse bias region. And the way to identify this state is as follows. You open up this Zener diode from the circuit and then find out the voltage drop across this opened out terminals. So let's call that voltage as Vp, and then we will compare Vp with the reverse saturation voltage of the Zener diode. So with a circuit like this is a very simple circuit given the fact that this is a single loop, and we can assume that the current that flows through this loop is small I. And using KVL, we can frame the loop equation as negative 3.7 plus 1 kilo multiplied by I plus 1 kilo multiplied by I plus 0.7 is equal to 0. And then instead of writing 1 kilo ohm, we can take the resistance to be in units of kilo ohm, so that current I will come out to be in units of milliampere. And so solving for this equation leads to small I being equal to 1.5 milliampere. So the current that flows through this loop is 1.5 milliampere. Now what about Vp? Vp is the voltage drop across this connection, because these are connected in parallel, and so we can write Vp to be the same as I multiplied by 1 kilo ohm plus 0.7 volt. So Vp becomes equal to 1.5 into 1 kilo ohm, where 1.5 is in milliamperes, plus 0.7 volt, and this is equal to 2.2 volt. So the voltage across this open circuited terminal is 2.2 volt. And so if the Zener diode was present over here, it will be somewhere around this point. This is negative 2.2 volt. But in order to reach the reverse breakdown region, you have to push it to be about 2.7 volt. So because Vp is less than Vz, which is equal to 2.7 volt, this Zener diode has not managed to move into this reverse conduction mode. This is over here, it is somewhere over here, and so the current flow through the Zener diode is zero. So it is in reverse non-conduction mode. And the equivalent model for such a Zener diode is an open circuit, because the current flow at this point is equal to 0 volt, 0 milliampere. So the output voltage V0 will be simply equal to whatever we had calculated for this circuit, because the presence of this Zener diode is not there, and therefore V0 is the same as Vp, which is equal to 2.2 volt. So the answer to this question is option C, which is 2.2 volt. Now note that a slight variation to this problem could be if I had a, let's say, a Zener diode which had a breakdown voltage of 1.8 volts. So in this characteristic curve, it will be something like over here, where this is negative of 1.8 volt. And so in that case, you can find that Vp, which is 2.2 volt, exceeds the Zener breakdown voltage. And so the Zener diode will then move into its conduction mode in the reverse region. And so the output voltage will get locked into whatever is the breakdown voltage of the Zener diode. So the output voltage V0 will then be equal to 1.8 volt. So the pattern of solution for circuits comprising Zener diode with DC inputs is same as what we have shown here. So here a single Zener diode is present. There could be questions where you can have multiple Zener diodes, but the approach to tackling this sort of questions remains the same as discussed in this question.